In this video, we're going to focus on learning target number 2, the first part. So I can describe the number and location of orbitals and electrons using quantum numbers. So just a quick review from what we went over the last time we had class. We were talking about the quantum mechanical model and the fact that we can actually predict where electrons are going to be by treating them like a wave. And Erwin Schrödinger came up with this idea, and he applied wave theory to figure out where electrons are going to be most of the time. We can't figure out where they're going to be all of the time and what we're doing because of Heisenberg's uncertainty principle, but he created these regions of probability using statistics to figure out if you were looking for an electron traveling at a certain energy level, where would be the best place you looked. Remember, these diagrams down here are grainy on purpose. Each one of these dots is an answer to where an electron is using Schrödinger's wave equation. And then he figured out where 95% of his answers were going to be. And because he did his calculations in 3D, he found this region of probability where you're going to find the electron. Now remember, this is not a container that the electron bounces around in. It's not a surface that the electron rides on. The electron could potentially be anywhere, but if you're going to look for it, your best bet is to find it somewhere in this region of probability called a quantum orbital. Now, depending on how fast the electron is moving, what energy level it's at, these quantum orbitals have different sizes and different shapes. And this is when we got into the s orbital. It's roughly spherical. P orbitals, they kind of look like peanuts in a shell. D orbitals, remember I naively call them daisy flowers because they have 4 lobes to them. And these F-shaped orbitals, I naively think they're F-shaped because they're freaking complicated. What Schrödinger then did was he invented a code, kind of like the mailing address if I wanted to send you a snail mail letter. It's a 4-digit code that tells you where the electron is and what is it doing and where you should look for it. Schrödinger called this digit code quantum numbers. The first quantum number he actually stole from Bohr. It's called the principal quantum number, and it's notated with a lowercase n. It describes how big the orbital is and how fast the electron is going. The higher the value of n, the more energy the electrons have, so the faster they're going, and the more likely they're going to be further away from the nucleus. Coding-wise, n always starts with the integer 1 and goes to infinity. So 1, 2, 3, 4, 5. The faster the electron goes, the higher the n value is going to be. One quick trick you can use if you want to figure out how many electrons are available to be in a particular energy level, you can use this math equation 2n squared. So in the first energy level, n equals 1, that means you can only have 2 electrons in that energy level. In the second energy level, you can have 8. This is where the 2-8-8 rule came from in grade 9. But you quickly notice that in the third energy level, you have more than 8. It actually goes 2, 8, 18, 32, and you can continue on if you want. The second orbital quantum number is called the orbital shape quantum number, and it's notated with an L. What that does is it tells you what shape the orbital is. And over here on the side, we have the code. If you have an s orbital, Schrödinger coded it as an L equals 0. P orbital, L equals 1. A d orbital, L equals 2. And an f orbital, L equals 3. And you need to remember this code. This part is a tricky one. What common mistake people make is they put s is equaling 1 because it's the first shape, but s actually is coded as a 0. There is this trick that Schrödinger did in his coding rules that you can figure out what possible shapes are available at each energy level. The possible L values always range from 0 to 1 less than n. So if you're in the first energy level, then L can only equal 0, which means there's only S-shaped orbitals available there. But when n equals 2, L can possibly equal 0 or 1. So in the second energy level, there's S-shaped orbitals and p orbitals that you can find electrons in. You notice as you go up each energy level, a new shape gets introduced. So the d orbitals only show up when n equals 3 or above, and the f orbitals only show up when n equals 4 or above. So with just these two quantum numbers, I can tell you where to look for an electron. I could tell you to look for an electron in a 3s orbital. Because n equals 3, you'd be looking for an electron that's moving in the third energy level, and quantitatively there's actually speeds attached to that value. We won't get into that into this course though. But if I tell you to go look in a 3s orbital, I'm asking you to search for an electron in kind of a medium-sized sphere. The third quantum number is called the magnetic quantum number, or the ML value. It describes what orientation or plane the orbital you're searching is on. What I mean by that is if you have p orbitals, you can actually stack them on top of each other. In terms of what axis they're on, you could have a p that's centered on the x-axis, you could have a p orbital centered on the z-axis, or you could have a p orbital centered on the y-axis. And each of those axes or planes of orientation are denoted by an ML value. ML values always get coded by them having them range from -L to +L. So let's say, for example, you have a p-shaped orbital, so L would equal 1. That means your ML values would be -1, 0, and +1. And that gives us these three diagrams. An ML of -1 means you have the p orbital on the x. ML equals 0 means it's on the z. ML equal 1 means it's on the y. Now in this course, you don't need to know that an ML value of -1 is a peanut on the x-axis. Maybe they'll make you memorize that in university. What's more important to us in this course is how many ML values there are in the range, because that tells us how many orbitals of that same size and shape you have electrons in. So if in a p orbital, you have 3 possible ML values, -1, 0, +1. That means there's always 3 p orbitals you need to search. P orbitals always come in a set of 3. D orbitals always come in a set of 5, like this diagram shows. Because if you have a d orbital, L equals 2, which means your ML values are going to range from -2 to +2, and there's 5 numbers there. They correspond to these 5 diagrams. F orbitals always come in a set of 7, because if you're in an F orbital, L equals 3, so your ML values would range from -3 to +3. That gives you 7 values. So we use these 3 quantum numbers to quickly describe where an electron could be found. I mentioned earlier that quantum numbers are kind of like your address if I would need to send you a letter. The N value is like saying you live in Ontario, Canada. The L value tells me you live in Orangeville, and the ML value tells me what street you live on. Notice there's a number missing, your house number. That's why we have a 4th number. Schrodinger didn't come up with that. That will be talked about in the next lesson. What I want you to do is just play around with the quantum number language using these coding rules. If I give you one value, you should be able to tell me the other numbers. To play with these numbers and this new language, Let's try some questions out on page 179 of your textbook. We'll do a couple of together first. Question number 1 says, for the quantum number n equals 3, what values of L are allowed? Well, we can use the internal coding rule to figure that out. If n equals 3, then L can range from any integer from 0 to 1 less than n. So that means the possible values of L are going to be 1 or 0, 1, or 2. The question further asks me, what are the ML values that are possible? Well, let's pick one of the values of L and work that out. Let's say L equals 2. If L equals 2, what are the possible ML values? Well, the coding rule says that ML always ranges from minus L to plus L. So if I start with minus 2 and write all the integers in between minus 2 and plus 2, that'll be my possible ML values. The question then asks us, and how many orbitals are there? To answer that question, we ask ourselves, how many ML values are in the range? There's 5 numbers between minus 2 and plus 2. That means there's 5 orbitals that are L equals 2 shape, which means they would be D-shaped orbitals, and n equals 3 big. Let's try out question 3a. What are the n, L, and possible ML values for the following orbital types? To name the orbital, we often just take the n value and put the shape of the orbital beside it. For example, this 2s orbital we're looking at. Well, if I'm in a 2s orbital, that 2 that's in front of the name is my n value, so n would equal 2. And because I have an s-shaped orbital, that automatically means L needs to be 0. Remember, the L value is coded by the shape. 0 is S, 1 is P, 2 is D, and 3 is F. Now for the ML value, they always range from minus L to plus L. So minus 0 and plus 0, that's the same number. It's just 0. Here's the n, L, and ML values for a 2s orbital. Let's have a look at 4b. What is the orbital type for this set of quantum numbers? It says n equals 5, L equals 3, and ML equals minus 2. The first thing we can do is figure out what shaped orbital it is. If L equals 3, that corresponds to having an F-shaped orbital, because 0 is S, 1 is P, 2 is D, 3 is F. To figure out how big this F orbital is, I look at the n value. That electron's moving in the 5th energy level, so it's going to be a pretty big F orbital. We would call it the 5F. I really like questions like number 9. The following set of quantum numbers are not allowed. Identify the problem and change one number to fix it. So if n equals 1, can L equal 2? No, that's a problem, because L can only be any integer from 0 to 1 less than n. But if L equals 2, can ML equal a minus 2? Absolutely. ML always ranges from minus L to plus L, so minus 2 is a possible number. So to fix this problem here, all I have to do is change this n equals 1 to any number higher than 3. So I could do n equals 3, n equals 4, n equals 7, and then that would correct the set and follow all the internal coding rules. Pause the video here and try out some more questions for about 15 minutes and see how you do at learning this quantum code. Work together in a group, try your best, and remember the answers to these questions are posted on the classroom if you want to double check to make sure you're getting them right.